The allowable resistance for a bonding conductor in a railcar unloading facility depends on several factors, including the National Electrical Code, industry standards, and specific facility requirements. Section 540.32 G of the National Electrical Code specifies that the resistance between the railcar and the ground rod should not exceed 0.1 ohms. The American Petroleum Institute recommends a maximum resistance of 0.5 ohms for bonding conductors in bulk liquid transfer applications. The facility's own operating procedures or insurance requirements may specify more stringent limits. Based on the above factors, a recommended high allowable limit for the resistance of a bonding conductor at a railcar unloading facility would be 0.5 ohms. This limit ensures that the conductor provides a low resistance path for static discharge, minimizing the risk of ignition. To measure the resistance of the bonding conductor, use a low resistance ohmmeter with a probe or clamp-on attachment. Connect one probe to the railcar frame and the other probe to the ground rod. The resistance reading should be below the allowable limit for the facility. Static electricity is a significant hazard in railcar unloading facilities, particularly when dealing with flammable liquids or gases. The accumulation of static charge can occur due to the flow of liquids, movement of equipment, or even atmospheric conditions. If this static charge is not properly dissipated, it can lead to a spark with sufficient energy to ignite flammable vapors, causing a fire or explosion. Bonding conductors play a crucial role in preventing static electricity hazards by providing a low resistance path for static charges to flow safely to ground. This prevents the build-up of potential differences between conductive objects, such as the railcar and the storage tank, thereby reducing the risk of a static discharge. The resistance of the bonding conductor is a critical parameter because it determines how effectively the conductor can dissipate static charges. A high resistance value indicates that the conductor is not providing an adequate path for the charges to flow, increasing the likelihood of a static build-up and a potential spark. Conversely, a low resistance value ensures that static charges can quickly and safely dissipate to ground, minimizing the risk of ignition. Maintaining a low resistance in bonding conductors is therefore essential for ensuring safety in railcar unloading facilities. Several factors can affect the resistance of a bonding conductor. Firstly, the material and size of the conductor influence its inherent resistance. Copper conductors, for instance, have a lower resistance than steel conductors of the same size. Secondly, the quality of the connections at each end of the conductor is crucial. Loose or corroded connections can significantly increase the resistance of the bonding path. Thirdly, the length of the conductor also plays a role, as longer conductors will have a higher resistance than shorter ones. In addition to these factors, environmental conditions, such as temperature and humidity, can also affect the resistance of the conductor. Regular inspection and maintenance of bonding conductors are essential to ensure that they remain effective. This includes visually inspecting the conductors for damage or corrosion, checking the tightness of connections, and periodically measuring the resistance of the conductor. Any issues identified during inspection should be promptly addressed to maintain the integrity of the bonding system. When measuring the resistance of a bonding conductor, it is important to use a suitable instrument and follow proper measurement procedures. A low resistance ohmmeter, also known as a micro-ohmmeter, is specifically designed to measure very low resistance values accurately. The ohmmeter should be calibrated and used according to the manufacturer's instructions. Before taking a measurement, ensure that the circuit is de-energized and that all connections are clean and tight. Connect the ohmmeter probes to the points between which the resistance is to be measured, such as the railcar frame and the ground rod. Take multiple readings and average them to improve the accuracy of the measurement. Compare the measured resistance value to the allowable limit specified by the applicable standards and facility requirements. If the measured resistance exceeds the allowable limit, take corrective action to reduce the resistance. This may involve cleaning or tightening connections, replacing damaged conductors, or improving the grounding system. Document all inspection and measurement activities, including the date, time, location, measured values, and any corrective actions taken. This documentation provides a record of the bonding system's performance and helps to identify any trends or potential problems. The National Electrical Code, or National Fire Protection Association 70, is a widely adopted standard for electrical safety in the United States. Section 540.32 G of the National Electrical Code specifically addresses the grounding and bonding requirements for railcar unloading facilities. This section mandates that the resistance between the railcar and the ground rod should not exceed 0.1 ohms. This requirement is intended to ensure that static charges can be safely dissipated to ground, minimizing the risk of ignition. Compliance with this requirement is essential for ensuring the safety of railcar unloading operations. The American Petroleum Institute is a trade association that develops standards and best practices for the petroleum and petrochemical industries. The American Petroleum Institute recommends a maximum resistance of 0.5 ohms for bonding conductors in bulk liquid transfer applications. This recommendation is more stringent than the National Electrical Code requirement and reflects the higher level of risk associated with the transfer of flammable liquids. Adhering to the American Petroleum Institute recommendation can provide an additional margin of safety in railcar unloading facilities. In addition to the National Electrical Code and American Petroleum Institute standards, specific facilities may have their own operating procedures or insurance requirements that specify more stringent limits for bonding conductor resistance. These requirements may be based on the specific hazards present at the facility, the type of materials being handled, or the insurance company's risk assessment. It is important to consult the facility's documentation and insurance policies to determine the applicable requirement. In the absence of specific facility requirements, a recommended high allowable limit for the resistance of a bonding conductor to a railcar unloading facility would be 0.5 ohms. This limit provides a reasonable balance between safety and practicality and is consistent with industry best practices. Maintaining the resistance below this limit ensures that the bonding conductor provides an effective path for static discharge, minimizing the risk of ignition. It is important to note that this limit is a maximum value, and it is always preferable to achieve a low resistance value if possible. A low resistance value provides a greater margin of safety and ensures that the bonding system is performing optimally. Regular monitoring and maintenance of the bonding system are essential to maintain a low resistance value over time. Measuring the resistance of a bonding conductor is a relatively simple process that can be performed using a low resistance ohmmeter. However, it is important to follow proper procedures to ensure accurate and reliable results. Firstly, ensure that the circuit is de-energized and that all connections are clean and tight. Corrosion or loose connections can significantly increase the resistance of the bonding path, leading to inaccurate measurements. Secondly, use a low resistance ohmmeter with a probe or clamp on attachment. These ohmmeters are specifically designed to measure very low resistance values accurately. Standard ohmmeters may not be sensitive enough to measure the low resistance values encountered in bonding systems. Thirdly, connect one probe of the ohmmeter to the railcar frame and the other probe to the ground rod. Ensure that the probes are making good contact with the metal surfaces. Fourthly, take multiple readings and average them to improve the accuracy of the measurement. Resistance measurements can be affected by various factors, such as temperature and contact resistance. Taking multiple readings and averaging them helps to minimize the impact of these factors. Finally, compare the measured resistance value to the allowable limit specified by the applicable standards and facility requirements. If the measured resistance exceeds the allowable limit, take corrective action to reduce the resistance. This may involve cleaning or tightening connections, replacing damaged conductors, or improving the grounding system. Regular inspection and maintenance of bonding conductors are essential to ensure that they remain effective in preventing static electricity hazards. Inspection should be performed at regular intervals, such as monthly or quarterly, depending on the severity of the risk and the facility's operating procedures. During inspections, visually examine the conductors for any signs of damage, corrosion, or loose connections. Pay particular attention to the connections at each end of the conductor, as these are the most likely points of failure. Check the tightness of all connections and tighten them if necessary. Clean any corrosion or oxidation from the conductor surfaces using a wire brush or other suitable cleaning tool. Measure the resistance of the bonding conductor using a low resistance ohmmeter, as described above. Compare the measured resistance value to the allowable limit and take corrective action if necessary. Keep a record of all inspection and maintenance activities, including the date, time, findings, and corrective actions taken. This record provides a valuable reference for future inspections and helps to identify any trends or potential problems. In addition to regular inspections and maintenance, it is also important to consider the design and installation of the bonding system. The bonding conductor should be sized appropriately for the expected current flow. The conductor should be installed in a manner that minimizes the risk of damage or corrosion. The grounding system should be properly designed and installed to provide a low impedance path to ground. All components of the bonding and grounding system should be compatible and properly connected. Following these guidelines will help to ensure that the bonding system is effective in preventing static electricity hazards in railcar unloading facilities. Static electricity can be generated by a variety of mechanisms in railcar unloading operations. The flow of liquids or gases through pipes and hoses can generate static charges due to friction between the fluid and the pipe walls. The movement of equipment, such as pumps and valves, can also generate static charges. Atmospheric conditions, such as dry air and windy conditions, can increase the risk of static charge accumulation. The type of material being transferred also affects the risk of static electricity. Flammable liquids and gases are more likely to ignite from a static spark than non-flammable materials. Materials with low conductivity are more likely to accumulate static charges than materials with high conductivity. The design of the unloading system can also influence the risk of static electricity. Systems with long pipes and hoses, sharp bends, or turbulent flow are more likely to generate static charges. Systems with poor grounding or bonding are more likely to allow static charges to accumulate. Understanding the mechanisms of static charge generation is essential for implementing effective static control measures. In addition to bonding conductors, other static control measures may be necessary in railcar unloading facilities. Grounding straps can be used to ground equipment and personnel to prevent static charge accumulation. Static dissipative coatings can be applied to surfaces to reduce the generation of static charges. Air ionization systems can be used to neutralize static charges in the air. Humidity control can help to reduce the risk of static charge accumulation. Proper ventilation can help to remove flammable vapors from the area. Fire suppression systems can be used to extinguish fires in the event of a static spark ignition. The selection of appropriate static control measures depends on the specific hazards present at the facility and the type of materials being handled. A comprehensive static control program should include a combination of engineering controls, administrative controls, and personal protective equipment. Engineering controls, such as bonding conductors and grounding straps, are designed to eliminate or reduce the risk of static charge accumulation. Administrative controls, such as written procedures and training programs, are designed to ensure that workers are aware of the hazards of static electricity and follow proper safety practices. Personal protective equipment, such as static dissipative clothing and footwear, can help to protect workers from the effects of static electricity. A well-designed and implemented static control program is essential for ensuring the safety of railcar unloading operations. Bonding conductors are a critical component of a comprehensive static control program in railcar unloading facilities. By providing a low-resistance path for static charges to flow safely to ground, bonding conductors help to prevent the build-up of potential differences between conductive objects and reduce the risk of static discharge. Maintaining a low resistance in bonding conductors is therefore essential for ensuring safety in railcar unloading operations. The allowable resistance for a bonding conductor in a railcar unloading facility depends on several factors, including the National Electrical Code, industry standards, and specific facility requirements. A recommended high allowable limit for the resistance of a bonding conductor at a railcar unloading facility is 0.5 ohms. Regular inspection and maintenance of bonding conductors are essential to ensure that they remain effective in preventing static electricity hazards. Following proper measurement procedures and documenting all inspection and maintenance activities are important for maintaining a safe and reliable bonding system. By implementing a comprehensive static control program and paying close attention to the performance of bonding conductors, railcar unloading facilities can significantly reduce the risk of static electricity-related incidents.